Special relativity. Time dilation. Consider a clock h' in frame k' located at coordinate x'(a). Clock h' is moving at a speed v relative to frame k. From the standpoint of observer k, all his clocks are synchronized. At time ta, clock h' is at location xa. The clock h' passes by a sequence of synchronized clocks in frame k until it reaches clock b at time t'b. So at time tb, clock h' is at location xb in frame k. When clock h registers time ta in frame k, the corresponding time it registers in frame k' is t'A. And when clock h' registers time tb in frame k, the corresponding time it registers in frame k' is t'B. Hence, the time period which elapses in frame k during the movement of clock h' from A to B is delta t equals tb minus ta. And the time period which elapses in frame k' during the movement of clock h' from A to B relative to frame k is delta t' equals t'b minus t'A. The coordinate of clock h' in frame k' is xa equals a. When clock h' reaches point A, its location xa and the corresponding clock reading ta relative to frame k are given by the following expressions, where x'(a) equals a. When clock h' reaches point B, its location xb and the corresponding clock reading tb relative to frame k are given by the following expressions, where x'(b) equals a. The difference in clock's readings between clock B and A can be found by subtracting ta from tb. This law will be written as delta t is equal to gamma times delta t'. From the standpoint of observer k, we can read this law as follows. The time period measured by two different clocks in frame k, which is delta t, is longer in duration than the time period measured by one clock in frame k', which is delta t'. This law can be applied only when observer k is using two clocks to observe one moving clock in frame k'. In other words, the tick-tock of moving clock is slower than the tick-tock of stationary clock. This is called time dilation. This law will be read by observer k' as delta t' is equal to 1 over gamma times delta t. From the standpoint of observer k', we can read this law as follows. The time period measured by one clock in k', which is delta t', is shorter in duration than the time period measured by two clocks in k, which is delta t. From the standpoint of observer k, clock h' has traveled a distance xb minus xa. Substituting t'b minus t'A in the previous relation, we obtain xb minus xa equals v times tb minus ta. And this is the distance between the two clocks in frame k. From the standpoint of observer k', clock h' has traveled a distance x'A minus x'A equal to 0. In fact, clock h' has been assumed to be fixed in frame k'. If observer k' is using two clocks to observe one clock in k, then the law should be written as delta t' is equal to gamma time delta t. In other words, the factor gamma should always be multiplied by the terms related to the time interval measured by one clock. The conditions according to which this law can be applied are: 1. Frame k is observing. 2. All clocks are synchronized in frame k. 3. Observer k is using two different stationary clocks to measure the reading of one clock in frame k'. 4. tb minus ta equals the time period elapsing by two different stationary clocks in frame k. 5. t'b minus t'A equals the time period elapsing by one clocks in frame k'. 6. The factor gamma should always be multiplied by the terms related to the time interval measured by one clock. Problem. A clock h prime is moving at speed 0.9 times c relative to reference frame k, where c is the speed of light. Both observers k and k prime use clocks which ticks every second. If observer k prime hears his clock h prime tick-tocking for 1 second, how many seconds this moving clock h prime will tick-tock for observer k? Solution: the difference in two consecutive readings or the tick-tock of clock h prime is delta t prime equals 1 second. Observer k will hear this moving clock h prime tick-tocking with longer duration. Delta t can be computed by substituting v equals 0.9 c in the formula of delta t. We obtain delta t equals 2.29 seconds. The result means that when observer k compares the rhythm of his stationary clocks, which tick-tock each 1 second, with the clock h prime, he will hear this moving clock tick-tocking each 2.29 seconds. Hence, a moving clocks will tick-tock slower than a stationary clock, or the tick-tock of a moving clock will dilate in comparison with a stationary clock. That happen when observer k uses two different clocks in his frame to listen to the tick-tock of clock h prime. The two clocks in frame k are spaced at a distance, xp minus xa. And we obtain delta x equals 2.6981 times 10 to the power of 8 meters. However, when observer k uses one clock to listen to the ticks of two clocks of observer k, he will hear the rhythm to be shorter in duration. Delta t prime equals 0.436 seconds. If observer k prime uses two different clocks to listen to the ticks of one moving clock in frame k, he will hear the rhythm to be longer than his own clocks, that is, 2.2942 seconds.